Welcome to the class of Control System 1. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. This class will discuss basic concepts of PI and PID controller and its different applications in industry. So, we will discuss today the automatic controller, classification based on the basis of control action, the pre-controller, integral controller, proportional integral controller, PD controller, and PID controller, and with different applications. So first start with automatic controller. And controller is a device which is introduced in feedback or forward path of a system which controls the steady state and the transient response according to the requirement. An automatic control or automatic regulator system is one that maintains the actual output at the desired value in the presence of disturbance or for a slowly varying reference input. This is a block diagram of automatic controller, and here the reference input is given and the amplifier portion produce the actuating signal which goes to the actuator or the final control element, and it operates on the process, and output of the process is taken from the plant is used as the measuring element or transducer, and it is connected to the error detector, and the error detector produces a signal which is applied to the controller is the algebraic sum or the difference between two different inputs of this error detector. And the manner in which the automatic controller produces the control signal is called the control action. These are the classification based on the basis of control action. First is the proportional controller, then integral controller, proportional and integral controller, the derivative controller, then the proportional and derivative controller, and finally the proportional integral plus derivative controller, that is the PID controller. So first consider the proportional controller. The proportional controller is a device that produces a control signal which is proportional to the input error signal. And the error signal is the difference between the reference input and the feedback. And this feedback is obtained from the output. That means portion of the output is taken as the feedback. And this is the block diagram of a proportional control system. And the actuating signal, that means this signal is proportional to the error signal. So we can write Ut is proportional to Et or Ut equal to Kp into Et, where Kp is the proportional gain. Next, we are applying the Laplace transform in the both sides. So it becomes Us equal to Kp into Es, or the Us by Es, that is the transfer function of this block, becomes Kp, and Kp is known as the proportional gain. The proportional controller amplifies the error signal by an amount Kp. Also, the introduction of pre-controller in the system increases the forward path gain by an amount Kp. Now, if the forward path gain is increased, the peak overshoot increases while the steady state error is reduced. Here, due to application of pre-controller, the steady state error is only reduced. Let's take an example. We have considered here that GS is a first order system and the transfer function is equal to K by 1 plus S tau. Now, if we find out the overall transfer function, that is Ks by Rl, and that becomes Kkp by 1 plus Kkp by 1 plus S into tau by 1 plus K into Kp. Whereas this K into Kp by 1 plus Kkp is the steady state gain, and this tau by 1 plus Kkp is the closed loop time constant. So, if we increase the value of Kp in this equation, then the tau will be decreased. That means Kp is inversely proportional to the time constant, and that means if Kp decreases, then the closed loop response speeds up. Next, we need to calculate the steady state error. And the steady state error for unit step input, we have applied the formula limit s tends to 0 SRS by 1 plus GSHS. And for the unit step input, this RS becomes 1 by S. So this becomes 1 by 1 plus K into K. Here also the steady state error is inversely proportional to the value of Kp, and when Kp is increased, then the steady state error is decreasing. But at the value of Kp at infinite, then only the steady state error becomes 0. So the difference of the process output and the set point goes to 0 when the Kp value is the infinite. That means it can reduce the steady state error, but it cannot be eliminated by using of P controller. That means there is always a difference between the output as well as the set point. So this steady state error, this type of error is known as the offset, which cannot be eliminated in using the proportional controller. Next is the integral controller. And in this integral controller, we can eliminate the offset error which was reduced in proportional controller but couldn't be eliminated. And here the type number is increased because this here the output of is proportional to the integral of the error. So ut is proportional to integration of pt or ut equal to ki into et, and this ki is the integral gain, and in Laplace domain us equal to ki by s into es, us by es, that is the transfer function of this controller, equal to ki divided by s. So if we use integral controller with a system due to the presence of the pole at origin, that if this is the type number of the system is increased. And here the forward path transfer function becomes k into ki by 1 s into 1 plus s tau if we consider this gs is equal to k by 1 plus s tau. And here if we check the steady state error, then it becomes s into rs, and here also rs is equal to 1 by s because we are considering the unit step input, then the steady state error goes to 0. That means the offset error or the steady state error can be completely eliminated by using the integral controller. And the presence of I action actually leads to the oscillatory and closed loop response, and it may lead to the instability. Next is the proportional and integral controller, that is the PI controller. And this PI controller is usually used in the maximum cases, that is 98% of the process industry is now using the PI controller. And PI controller is used in industrial applications due to its simple structure, and it is very easy to design, and due to its low cost. But it fails when the control object is highly nonlinear and uncertain, and it eliminates the forced oscillations and steady state error. However, introducing the integral mode has a negative effect on the speed of response and overall stability of the system. So the PI will not increase the speed of the response, and it can be expected PI controller does not have means to predict what will happen with the error in the near future. And using of PI controller can make the system more sluggish and oscillatory. And the type and order of the system is increases due to presence of this integral term. So this is the proportional and integral controller, whereas the transfer function becomes Kp plus Ki by S. Next is the proportional and derivative controller. And the derivative control, which is also known as the predictive control, because it can predict the error what is what will be happen in the near future, because it uses the extrapolation, and once the derivative mode has predicted the future error, it can add the additional control action which is equal to the controller gain into the future error. But if the error becomes 0 in a derivative control, then the derivative controller has no output. because in derivative controller it is proportional to the derivative of the error. So if the derivative of the if we derivate a constant, then it becomes 0. So if the error is 0, then derivative control has no output. So it cannot be used single, and it is always used with the combination of P controller, that is the proportional plus derivative controller. And the derivative control is used to reduce the magnitude of the overshoot produced by the integral component and to improve the process stability. And the D action does not affect the steady state error but affect on the transient response. So here both the proportional part and the derivative part is present, and ut is equal to kp into et plus kd into derivative of the error. And in Laplace domain, we can say that U is equal to Kp plus Kds into Es, or the transfer function becomes Kp plus Kd into S. The derivative control can predict the error in future based on the current scope of the error. And we have considered that the derivative action time, that is equal to ratio of Kd by Kp. And once derivative mode has been predicted the future, it can add an additional control action. For an example, the error changes at rate of 2% per minute and the derivative time PD is given as 3 minutes, and the predicted error is 6%. The controller gain is considered as 0.2. Then this derivative control mode will add an additional this 0.2 into 6%, that is 1.2% to the controller output. As it can predict, hence this action is also known as the predictive control. Next is the PID controller. From the name, you can see in the PID controller, it is a 3-mode controller, and both the integral action, the derivative action, as well as the proportional action is present. So it has all necessary dynamics, that is fast reaction on change of the controller input, and its error minimization, and the suitabilization inside the control error area to eliminate the oscillations. That is the P mode. Now, the transfer function has all the 3 parts, that is Kp plus Ki by S and plus Kd into S. And if we find out Us by Es, then it becomes Kp plus Kds plus Ki by S. Now these 3 are parameters of proportional controller, that is Kp, Ki and Kd, and if we increase the parameter values, then it has directly effect with the system parameters, that is the rise time, overshoot, settling time, steady state error. So for an example, if we increase the Kp values, then we can see from this table that the steady state error has been decreased but cannot be eliminated, whereas using of Ki, the steady state error can be eliminated. And both for Kp and Ki, if this increases, the overshoot increases, whereas using the Kd, the overshoot has been decreased. And for the settling time, if we increase the Kp values, there is a very nominal change, but use of integral term, the settling time is increased, whereas due to the Kd term, the settling time has been decreased. So this is the overall effect of increasing these parameters in the rise time, overshoot, settling time, and steady state error. Next is the applications of these 3 type of controllers, PPI and PID controller. Now in industry, the maximum use is the PI, that is the 98% of use, but PID can be used almost 95%, whereas the P has only limited applications in industry. So only P control is suited for many cascaded applications as it provides an effective means for counteracting upstream process disturbances. Within the cascade architecture, the controller output of the outer loop serves as the set point of the inner loop. The inner loop is able to see and react to disturbances ahead of the outer loop, and when tuned, Using only the P configuration, the controller is able to react faster than the outer loop and thereby check the burn of disturbances. While overshoot can be expected, its impact is confined to the inner loop. Any offset associated with use of a only P controller is typically corrected by the outer loop as long as the outer loop is not excessively slow. And another industrial application of P controller is surge tank level control. And a surge tank is designed to protect other downstream process from the negative effects of upstream disturbances. And surge tanks routinely apply level control to mitigate harmful variability of liquid as it flows downstream. And when configured with P-only controller, a surge tank is able to respond effectively to large incursions of liquid and it is easily tuned for the suitable level control. Next is the application of PI controller, and the first one is the liquid flow control. And many processes such as the liquid flow control are ideal applications for the PI control, and they are critical to maintaining production rates such as any extended periods of offset associated with P-only control and counterproductive. And they also possess exponentially fast dynamics for which the derivative provides little to no benefit. And for this and many other flow processes, the PI control effectively mitigates offset and it can be used and it has excessive variability in response to the process noise. Another application is steam pressure control, and pressure is another process type that is often essential to production and it exhibits highly dynamic characteristics. With steam pressure control, the prevailing objective is to react quickly to change in demand from the downstream users while limiting a negative effects of sensitive process instrumentation. The P-only control alone is unsuitable as it is unable to adequately track the set point. The PID control routinely comes to excessive variability due to the noise. Whereas we can use the PI control because it delivers improved set point tracking and does not subject instrumentation to unnecessary wear and tear. And another example of PI applications is the heat exchanger temperature control. And heat exchanger temperature control is temperature of a heat exchanger must be controlled within a relatively high tolerance. And alone the P only control may be an option, but the heat exchanger dynamics is sufficiently fast such that the derivative is unnecessary. So we can use the PI controller over here. Next, the applications of PID controller. One is application is the furnace temperature control. It's commonplace for the material involved to have a large mass because the furnace typically involves heating and holding large amount of raw material at a high temperature. And as a result, it possesses a high degree of inertia. The material's temperature does not change quickly even when the heat is applied. And this characteristic results a relatively steady process variable signal and it allows the derivative term to effectively correct for the error without excessive changes to either the controller output or the final control element. Another application is the neutralization of pH control, which is widely viewed in the industry as a challenge to control because pH is highly nonlinear and its behavior changes from one operating range to another. The buffering effects of some material can curb what would otherwise be volatile dynamics until the buffer is saturated. While the dynamics of pH are challenging from a control perspective, they are well suited for PID controllers, and specifically the dynamics of pH tend to be slow as the amount of acid that's typically added to a process is relatively small when compared to the volume of existing liquid. And the slower dynamics allowed the derivative to improve the control without overworking with the final control element. And another application is the batch temperature control. And here the bubbling and other process noise will certainly be the noise has a less issue in the closed loop system, and batch temperature control relates to temperature itself because the heat can be added but it cannot be subtracted in heat temperature control. The net effects, the dynamics are both slow and non-linear and the noise is limited. Then these characteristics make for an ideal application of PID controller. So these are the industrial applications and these are the references. Thank you.